Large language models excel at understanding and generating human-like text, but there's a catch. We often assume they know everything they've been trained on, storing vast factual knowledge right inside their parameters.
Right, like ChatGPT knows about history or physics because it's in its weights, but sometimes it makes things up, or it's just plain wrong about recent events.
Exactly. That's the core tension RAG addresses. These models are great at language, but their ability to access and precisely manipulate knowledge is still limited.
So even if the information was in its training data at some point, it can still struggle to retrieve it accurately when needed? And if it's not, it can just invent it?
Yes, and another problem is the why. LLMs can't easily tell us where they got their information, making it difficult to trust or verify. Providing provenance for their decisions remains an open problem.
That's a huge issue for reliability. If I can't check its sources, how can I use it for anything critical?
This paper introduces a general-purpose fine-tuning recipe for retrieval-augmented generation, or RAG. It describes RAG models as ones that combine pre-trained parametric and non-parametric memory for language generation.
Parametric and non-parametric memory. So the model's internal knowledge and then something external?
Precisely. Think of the LLM's parametric memory as its learned weights, the knowledge baked in during training. The non-parametric memory is like a dynamic external library it can consult. This is exact in that it's external and consultable, but unlike a human librarian, it retrieves based purely on semantic similarity of encoded text, not on deeper conceptual understanding.
Like a student with a textbook open during an exam, rather than just relying on what they memorized? How does it access it?
The analogy holds for the ability to look up facts, but breaks because the LLM isn't reading in a human sense. It's being provided with text snippets that influence its next word prediction based on its statistical understanding.
The original RAG paper proposes a specific setup. The parametric memory is a pre-trained seek-to-seek model, like a transformer encoder-decoder. And the non-parametric memory is a dense vector index of Wikipedia, accessed with a neural retriever. The neural retriever is a separate model, often another transformer encoder, trained to take a query and embed it, then compare that embedding to a vast index of document embeddings to find the most semantically similar pieces of text. So the LLM itself plus a searchable vector-based database of external information.
Exactly. We've talked about transformers and attention in case number TCM-183004. Here, that seek-to-seek model is a transformer. The key is how it leverages an external source, rather than solely relying on its internal frozen weights.
That makes sense. It's using its language understanding to find relevant information from outside.
And the results were significant. On knowledge-intensive NLP tasks, like open domain question answering, RAG models achieved state-of-the-art results, outperforming parametric seek-to-seek models and task-specific retrieve and extract architectures. They were also found to generate more specific, diverse, and factual language than models relying solely on internal parameters, showcasing a clear improvement.
So better than just a large language model, and better than systems designed specifically for retrieval and extraction alone, and more trustworthy.
It was a clear improvement, but why is this external memory so crucial for LLMs? Let's dig into the common pitfalls of models without RAG, and then how RAG directly solves them.
I'm curious to see the specific problems it fixes. The hallucination issue is definitely a big one.
The core problem RAG tackles is what this article calls confidently inaccurate and irrelevant output from LLMs. We call this hallucination. The model invents plausible but false information.
It's like they're trying so hard to be helpful and fluent, they'll just make things up if they don't know the answer instead of saying, I don't know.
Exactly. One major reason is the knowledge cutoff. LLMs are trained on massive data sets up to a certain point in time, then their weights are frozen.
Like a textbook that was printed 5 years ago? It's full of great information, but anything new won't be in there.
That's a perfect analogy. The data is frozen at a specific point in time, the cutoff. So asking about last week's news or a brand new product feature will often result in outdated or fabricated responses.
So the model literally can't know about current events because that information wasn't in its training data.
Another limitation, LLMs lack depth in domain-specific knowledge. While they have broad, general knowledge, highly specialized topics may not be adequately represented in their training data.
So it might know a lot about general medicine, but not about a rare genetic condition a specialist would know instantly.
And critically for many businesses, LLMs lack private or proprietary data. Imagine trying to get an LLM to answer questions about your company's internal policies or customer data. It simply can't.
Because that data was never part of its public training set, for good reason. It wouldn't be private anymore.
This leads to a loss of trust. Models typically cannot cite their sources related to a specific response. If you can't verify, you can't rely on it.
It's like a student who gives you an answer but can't tell you where they found it. You'd be suspicious. This is exact for the trust issue, but a student might genuinely forget their source. An LLM without RAG simply doesn't have a source to forget, as its knowledge is diffused across its parameters.
This is where RAG comes in. The article defines it as a technique that uses authoritative external data to improve the accuracy, relevancy, and usefulness of a model's output.
So instead of just relying on its internal memory, it gets to look things up in a reliable external library.
Yes, and it does this through 4 core components. First, ingestion of data, then retrieval of relevant data based on a query, followed by augmentation of the prompt, and finally, generation of the response.
That sounds like a clear pipeline. Get the data in, find what's needed, add it to the prompt, then generate.
It is. Now that we have the intuition for why RAG is necessary, let's go into the mechanism of these 4 steps. How do we actually prepare and retrieve that external knowledge for the LLM?
I'm especially interested in how the retrieval part works to get the most relevant information.
The RAG process begins with ingestion. This is where your external authoritative data, be it documents, PDFs, internal wikis, is prepared to be searchable.
So getting all the source material ready, even before a user asks a question.
A crucial part of ingestion is to chunk the data. You divide larger documents into smaller, manageable pieces, like breaking a book into paragraphs or sections. A common approach is to split text into fixed-size chunks, like 256 or 512 tokens, with some overlap, like 50 tokens, to preserve context across boundaries.
Why not just feed the whole document? Is it about finding really specific information?
Precisely. If chunks are too big, you might pull in too much irrelevant information. Too small, and you lose context. You choose a chunking strategy based on your data and expected queries.
So the analogy of a student with a textbook is exact here. You wouldn't hand them the whole library for one question, but one relevant page is better than one word. This is exact for the goal of optimal granularity, but the sections for RAG are often based on token counts or character limits, which might not always align perfectly with human-defined semantic boundaries.
After chunking, you create vector embeddings for each chunk. An embedding model converts each chunk into a numerical representation of the data's meaning. These embeddings are dense vectors where semantically similar texts are located closer to each other in a high-dimensional space, generated by the embedding model to capture context and relationships of words.
Ah, embeddings. We covered these with transformers in case TCM 063003. It's how computers understand the semantic meaning of text.
Yes, but here the purpose is explicit retrieval. This allows computers to search for similar items based on the vector representation of the stored data, meaning semantic similarity, not just keyword matching. This search typically involves calculating a similarity metric, like cosine similarity, between the query's embedding and the embeddings of all chunks in the database. The chunks with the highest similarity scores are considered most relevant.
So, if I ask, tell me about recent space missions, it can find chunks about Mars rover landings, even if I didn't use those exact words?
These vector embeddings are then load data into a vector database. This database is optimized for fast similarity searches, allowing quick retrieval of relevant chunks. Vector databases are specialized to store and efficiently query these high-dimensional vectors, often using approximate nearest neighbor (ANN) algorithms to quickly find the closest vectors without having to compare against every single one.
This happens offline, right? You build this knowledge base once, then update it as needed?
Once a user submits a query, the retrieval step kicks in. The user's query is also embedded and then used to perform a semantic search to find the true meaning of the user's query.
So it finds the most semantically similar chunks from the vector database. These are the relevant passages from the first paper?
Exactly. Next, the augmentation step combines the retrieved chunks with the user's original query into a single enhanced prompt. For example, it might look like, here is some relevant information. Retrieved document 1, retrieved document 2. Based on this information, please answer the following question, user query. This provides the LLM with direct, verifiable context for its generation. And finally, generation. The LLM uses this augmented prompt to generate output. Because it has relevant authoritative information directly in front of it, it can provide more accurate, specific, and trustworthy answers.
And ideally, it can even cite the sources from the retrieved chunks, solving that provenance problem we talked about.
Precisely. This entire pipeline significantly boosts the reliability and utility of LLMs. However, like any advanced technique, RAG isn't without its own set of considerations and limitations.
I'm sure there are trade-offs. What should practitioners be mindful of when implementing RAG?
While powerful, RAG isn't a magic bullet. Its effectiveness hinges on the quality of the retrieved information. If your source data is poor or your chunking/embedding strategy is flawed, RAG can still produce irrelevant or incorrect responses. There's also the computational overhead and latency introduced by the retrieval step, and the LLM's finite context window limits how much retrieved information can actually be utilized.
So garbage in, garbage out still applies to the retrieval system, and you need robust processes to manage and update your knowledge base for accuracy and timeliness. And even with RAG, the LLM still needs to synthesize information and avoid its own biases. It's an enhancement, not a complete replacement for robust reasoning.